beginning of the recording that I think would be helpful.
Okay,
Jonathan, what did you want to say?
Well, I think it's to do with the heteroscedasticity.
Excellent. Did you? Oh, yeah. Gaith, is there time for him to present on that?
Yes.
Excellent. Okay, so I'll give an announcement. Then Jonathan will present for his team of heteroscedasticity friends, if I've said it right, and then you go on. Does that sound like a plan? Excellent. Tell me when. Is it when? Are we recording?
Yes, we are.
Oh, hi, everyone. Hey, sorry, little technical difficulties this morning. I just wanted to announce that I've set up two tech time talks. They're mostly aimed for the class, but they're a little more open too. But if we have class related questions, we'll cover those then. They're Wednesday mornings at 8 a.m. Mountain Daylight Savings Time in the USA. So please translate. That's 7:30 IST. It's 4 p.m. Central European Time. And then the same time on Saturday mornings right before this class. I'm doing both those times just to get the best coverage possible. And then the very brave and top student of the class, Jonathan Papworth, is going to present on, if we can even say it right, heteroscedasticity.
Yeah. Okay. Now, let me know if you're able to see the screen at all.
Yes, we can see.
Hope it's sharing. Is it zoomed in enough as well? I hope.
A little, if you can zoom a little, please.
Try and zoom in a little bit for you. Oh, my wheel isn't working on the mouse. Oh, there we go.
Awesome.
Is that better?
Yeah. It's awesome. Thank you.
Okay. So so we had the good. Sorry. So we had a little task to define the heteroscedasticity and what is it and what is the effect. So it causes bias in our model that pushes out the variance against the regression. So as we started off with a clean model where everything is close to the mean, over time it starts to push out. And then when we start to see that movement away from the mean over the x-axis, we should then start to reconsider looking at our model again to see what's causing those differences to happen over time. So it could be, then we go back into, is it a concept drift or a data drift that's causing that shift in the model? So I have some small diagram there where you can see the effect of the variation happening. So you can see that it's the points or the observations are moving further away from the mean as it goes further along in the x-axis.
Will you pick some name?
Okay. So yeah, we had a bit of coding to do, and we had the list comprehension from Tom, which is our actual model itself. And we had to look at the different variables going into the model and creating the fake data. And I just created a function here to make the plots and a function here for creating the envelope so we can understand the effects on the model as we put in different variables and what effect is having it push the observations away from the mean. So how I managed to interpret all of this. So we have the weight, which is causing the direction of the correlation. Is it standard? Is it negative? Or is it a positive correlation? I'll show some examples in a minute. Then we have the noise amplification. Then this here, we can affect the data points that they're moving away from the mean. And then the y-intercept is where we're starting on the y-axis. Are we starting the intercept at 0, or are we starting at 100? And then we have the envelope weight, which is causing a bit more of the bias into the model. And we have two points, the intercept of the model and the weight again, which is both of these. This one here, the weight is going to reduce the coefficients in our model. So,
Jonathan, real quick, is this this is a Markdown file? Oh no, great. One thing you can do so that we can read the rest of line 8, if you put a backslash right in front of your envelope function call, backslash, the other way, the other slash. There you go. Now we can see everything. Going ahead and hit enter there. Yeah. Now we can see the whole thing. And you may not, because this is inside square brackets, you may not even need that backslash, but I just want to say real quickly, kudos on the way you defined a function, and then you have the noise, but then you have a separate noise amplification outside the function. I love that. That was really smart of you.
Thank you. I was just trying to find different ways because I could go into the list itself, and yeah, I think it's good that if we're going to create models like this, it's better to keep the formula within the list comprehension, change the variable sizes outside, so then it's easier to locate as well.
And then one other request I have for you, we've already linked your GitHub repo in the top README file for the class. If you would please be so kind as to add a location for this notebook into your course notes, that way everybody can get back to this very quickly and easily. This is very good.
Okay, so let me just now run a few cells, because I don't want to run everything a bit further down in the notebook. I had some more practices on other things. So, okay, let's see. So this is just running now. So you know, we could ask the question. This is really showing really strongly that there's heterodicity in our model. We're quite close here, and then it just totally spreads further out. So if I'm just show this one here, the y-intercept, you see we're starting at 0. Everything goes well. Just do a small change. You see how it shifted now. We are actually at 5, but because of the scale of the y-axis, maybe I can just do a bigger shift on here. You see, we're starting to shift up where we're starting on the intercept. And then if I change this to a negative, you see we'll create the negative regression, or the negative in the model. And if correct, then we have the, I can make this one here. Then there's the no correlation, so it's just a straight midline going through the middle. So what we can start now is saying we can change the differences as well. So as you notice with what I have put in here, I also pulled up the correlation coefficients while playing around with our model. So then as we start drawing closer to the center, we should start to see that coefficients change as well. So if we can just reduce these to 1.
Now, Jonathan, forgive me for time's sake. This is so good. Oh, very nice.
So then now we've got a stronger coefficients.
everybody with me. This was outstanding. And Jonathan, this is so good. Jonathan, quick question. Was this a little hard?
To understand it, yes, I understand what the variables were doing into the affecting the model. Only knowing the simple linear regression, but creating it with fake data and understanding how to manipulate that data was quite difficult to start with. Yes.
Was it like a difficult hike where you had to hike up a steep point so you could see this beautiful view? Is it a beautiful view for you now?
It's definitely, yeah. You know, it's put into the different parts that I've learned previous to this with regression. This is kind of starting to make it a lot more clearer on how what's going to affect our model.
So the pain made you grow.
Yes. Yeah.
Now, guys, when you get in and play with this, each time you visit it, just try to understand one thing a little bit better. Ask me questions, ask Jonathan questions now. This was so good. So I'm not into giving grades, but I have a comical grade for you, Jonathan. This was a 99. The only reason I took off 1 point, and you can see how important this was to me, you didn't pronounce it right. At 1 point, heteroscedasticity, but I'm not even sure I'm saying it right. I give myself a -1 every time I say it because of lack of confidence.
Yeah.
Okay.
But the other question back to you, Tom. Am I, you know, and this is really important for the class with the interpretations of the variables into the formula.
Oh, this was great the way you set this up with these parameter values and the way you defined the function, the envelope function. That was just superb in my opinion. The other control I want people to see is it's that random variable, the ability for it to switch signs that's causing the envelope to be on both sides. So it actually is splitting off from the 0 point. But okay, we need to give plenty of time for Geith now, but that was outstanding. And I encourage everyone to follow Jonathan's example for the future and ask to do good presentations. All right, Geith, please take over.
Okay. Just a little confirmation about the sound. Is it better now? Okay. I will, before sharing my screen, I want to make a small introduction about what we are going to do today. Today, I want to move from the fake data to the real data first. I want to touch also again the healthcare sector. And I want to make this session as a landing for the next session, which is about the data balancing and the data imbalance, how to process one of the major issues in the data that we can face on the deep learning scenarios. Now, just to make, I think I have 5 minutes, I'm able to create introduction about the convolutional neural networks. Now we have the mathematical function, we can make it as a model. It will be if we name it a neuron or a node, and then we stack multiple neurons on one line. So we reach to a layer, and then when we stack layers with different size of a neuron, we reach to the neural network. This is the standard neural network building. At the end, all of this together is performing one task. Then at the end, or even if it's multitask, it will be a model also. It's mathematical model, but it's more complex. And when we go deeper and deeper in the layer, we reach to the deep learning scenario that using a huge size data, huge amount of data with a huge structure for neural networks. Now, if we are processing images, here we have to think about it in a different way. For example, if we have image by with the size of 255 pixel to 255, and it's colored RGB image, that means we have 3 channels for it. So the size or the pixel numbers count of this image, it's almost over than 195,000 pixel. If we are going to implement or enter this input to a neural network, that means the input layer for us, it will be only 195,000 neuron in the input. And then if we are going to connect this to the second layer and it's fully connected, we will find that this number, it will be to find the parameters, the weights and the pairs for it. It will be a huge number of parameters for this neural network to perform. Now, let's say we are lucky that we have kind of image processing appeared before that. I will explain one method about the image processing, and then we will see how the convolutional networks appeared. I'll share my screen now. Okay, let me go to full screen because I will move from different things. Now, let's consider that we have this image, which is small image 5 by 5, okay? And then we have a kind of filter we want to implement. Now, this filter can make different tasks. For example, can make edge detection. Now, each image, when we are taking image, it's because of the lights and the shadows, it shows some edges for the objects in the image. Now, we have a kind of method that helps us to make the edge detection, to detect this edge in the image. So we can find, let's say we can find the outlines of the shape. Now, how to do that? In fact, the edge detection, it's use the filter. Now, this filter is not edge detection, but it's I'm just using the edge detection just as example to the filters. It's this filter, it's another image with 3 by 3, for example. The values, it will be 0 or 1, depending on if we are trying to detect the vertical or horizontal or the slide image, the slide slope, edges. So the 0, for example, if we are looking for vertical edges, we can find that it will be zeros on the first column, ones on the second column, and zeros on the third column. Now, this window, this 3 by 3 image, we are going to just slide it over the image from the beginning to the end and make a multiply to convolve the values of the original image into smaller, or sometimes we can make some tricks to keep it on the same size, smaller image, but highlighting the edge according to that. Just like what we are showing here, that we have the window is moving from one place to another according to the size of the image and the size of the window that we are sliding this window, so we can find the values appeared on the convolved features. Now, this convolving, it's this, we are talking about, let's say, only one single channel image. That means it's maybe white and black, or maybe it's grayscale. Now, in our images, we have 3 channels. That means RGB for red, for green, for blue. Okay, the filter at that time, it will be also with the 3 channels. That means 3 matrices with 3 by 3. So in this way, we moved from one image in some size to another image to just convolve some features might be helpful on understanding the image content. Now, this algorithm, it's already there. It can be performed without using any neural networks, no need for it. But if we enhance it to include it into neural network structure, so what we are able to do, we have the image and we have a set of filters, all kind of filters, not only edge detection. We have plenty of filters can be used. Now, according to that, we will run this filter over the data that we have. And at the end, we will find that we reach to another image as a result to this. Now, this is a kind of model, but this model at the end is changing the size of the original image. The output is different from the input most of the time. We have at the end, we have some tricks. I'm not going to mention it here, but all the links, all the sessions that helpful, it will be also available in the repo. So I will add all the links to that. There is because I don't want to go deep on the convolutional neural networks. I just want to understand how the idea is appeared only. Okay, so now once we move from one image to another, until now we just use something called convolving features. Now, how to make it as a convolutional layer? That means it will be layer in the data in the neural network. In this way, just we have to run the same function that we used to run it. Now the image, the output of the image, it can be added to the PS, the values in each pixel. We can add one PS to it, and at the end we can run any function just to make it non-linear function, just like reload or other function, and we finish with a convolutional layer with output of neural networks. Yes, Tom.
Just real quick, I'm always trying to be sensitive to the way I was when I was new to this stuff, and I think, Guy, just correct me if I'm wrong. Just try to understand high level at this point. With this pass, no one could understand how to implement this yet. This is I think it's excellent Guy is going over this at this level, because when we get into the details of this kind of stuff, it will make a lot more sense. But we're not doing any math or code yet. So if you're feeling a little lost, it's probably because, and I'm saying this from personal experience, don't get wrapped up in the details yet. Just try to understand the high level conceptual that he's passing these kernels, these smaller matrices over these bigger matrices to look for characteristics in those small areas. And Guy, please correct me if I spoke out of turn.
No, you there is nothing wrong. It's perfect. But I want to show something. Right now, I'm focusing on the concept. The math, it will be on the linked videos, and the code, somehow it will be on this session and other session for our scenario. So we will show the code here. So just this is my plan about this. And also for sure with the next session with our friend Sadiq, who will join us. Now, what I want to say about this, now we are creating what is the benefit of using this method? We just remember the number that I told you about. If we have 255 by 255 image, we need 195,000 parameter and more. It's not only this, just to pass for the first layer, from the input layer to the first layer. Okay, it depends on the size of the first layer. Now, when we run these filters, we are able to shrink the image size with extracting some features from the image with less amount of parameters, because the parameters in this way, it will be related to the filter that we are using, the filter and the filter count. So this will give us better usage for the resources that we have. This is the main trick and the main reason of using convolutional neural networks, because it's helping us to process the huge data like images. Okay, think about it. We have filter, two filters, let's say, or one filter. It's 3 by 3. Okay, now even if the image it's 1000 by 1000 image, how many operation I'm going to perform to find the new image that run this filter? I only have 9 values, which is the values in the filter itself. Okay, and these values, it will be repeated for each value in the image. So I reduce the size of the parameters on this time very much. Now, this is the convolutional layer, which is filters, and then these filters will give me another value, another image, let's say, or another, let's name it output. And this output can be, we can run over it, we can run a non-linear function to make it as output of any neural networks with PS also. Now, when we stack some convolutional layer one by one until we are happy with the result, we can go, and because the image of the size, it's totally different right now, we can go to the fully connected layers, then standard way of understanding the neural networks, and then go to the output. So the structure of the CNN, convolutional neural networks, it's a set of conv layers, convolutional layers. And this, then there is something called max pool. I just please note it and read about it. And I will provide the links to it. What is the max pool and what's the difference between the max pool and average pool and the convolutional layer? What is the difference between these three concepts? And then when we are happy with the size of the image, we can go to the fully connected neural network to get the results or the output that we are looking for. So, and the target is reducing the resources usage and speeding the training. This is the target for the convolutional network. Now, what is our use case today? Our use case, it's a malaria detection model, something we will try to use convolutional neural networks that processing a segmented blood cells, red blood cells images to determine that this cell is infected by malaria or not. This is our task. The dataset that we have, it's already from TensorFlow dataset. It's open source dataset, we can use it. It's contain 27,000 image for this cell already segmented. That means we are not going to make image segmentation, which is different task. Okay, so I make it on Google Collab and it will be for sure available on the repo because I want Sadiq, our friend, to be able to continue working on it. So that's why I will keep it for Collab and he can continue working on it. And then we can use it on the IDE and see what we are going to do. But this Collab, I will split it. I'm not going to publish it right now to all because at the end, I'm using something to profiling and serving. That means to the end of the pipeline. So this this use case, it will continue appear in our sessions from time to time, depending on the task that we are going to discuss. Anything from anyone before continue explaining about what we perform here?
Real quick, I want to say, I feel like this explanation is very good, but magically what I've always found, if you go look at a few other references on convolution and kernels and the terminology that Geith has used in this lecture, just reading it from multiple viewpoints will help clear things up. But I would encourage you all to just stay at a high level for now.
The reason of staying on the high level, because if we are going on depth, we will lose the target of automated pipeline and we will focus on the model. That means we will go from the data-centric process that we are looking for and we will go to the model-centric process. So that's why I will keep this task for you. If anybody is not familiar with this modeling method, he can go and read about it. And the material is already there. It will be there on the repo by tomorrow, hopefully. Now, first we have the structure of this file. It's like the following. First, we have the imports. I'm adding all the imports in one place. So, for example, what is the BIL? BIL is Python image library. It's library that help us to import, manipulate, save the images, make a lot of play with the image in an easy way. NumPy, I think it's clear right now. I don't have to speak about it. What is, by the way, import OS, operating system, RE, it's regular expression. Now, for regular expression, it's a kind of encoding method that help us to match if the script that we have or the text that we have is matching, let's say, a template or matching, it's following a kind of template or not. So regular expression, sometimes it will be useful and it will be useful in our case. That's why I added here. JSON, I will speak about it later because it's not today. It will be later. What's the JSON? TensorFlow, because in this example, I use TensorFlow a lot. TensorFlow is a framework that helps us to automate and let's say interface all the machine learning methodologies and algorithms. Inside TensorFlow, we have Keras. Keras, it's especially for artificial neural networks That means it's another interface, but not for the full machine learning, especially for the neural networks. And there is 2 or 3 new things it will be used later. TensorFlow extended, which is help us to publish, deploy, and serving the model and monitoring it. And we have also another 2 tools, the TensorFlow Profiler. Profiler is a tool that keep monitoring the performance of the model, and we have Tensorboard that help us to show this performance. So this will be used later. Today we are not going to speak about it, but in this example it will be there. That means these tools. Now there is something we are focusing on it just to explain what is the math behind each and every step, what is the basic behind it, and also we need to take care about these tools. In this model, we used VGG 19. It's a kind of convolutional networks that consist of the following. I think, if I didn't know, this is about the Tensorboard. So this is what Tensorboard is providing to us. So if somebody want to read about it, but we will cover it later on the class. The VGG is VGG 19. It's a deep neural network that consists of 19 layers. This 19 layer is like the following: 3 convolutional layers, and then 1 max pool, another 3 convolutional layer, and then 1 max pool, another 3 convolutional layer from different sizes, and 1 max pool. And this will continue for the 4th time. And then we have 3 fully connected layers, finish with the softmax. Now, what is the softmax? When we are talking about the output, we will discuss about it. But today, our speaking will be on the data. So that means it's in the input. So what we are going to do here. I will run this import first. By the way, this Collab, if you use it immediately when I share it with you, it can use the GPU if you use it from the drive. If you host it locally, then this something it will be different. How to make the settings for it, it's different. Now, also we'll install this Tensorboard plugin profiler. That means this is, I speak about the profiler that help us to monitor the performance of the neural networks of the TensorFlow model. And we speak about the board, Tensorboard, that's helping us to show. Now the board and profiler, they are integrated to each other. So just we need to install this. This is for future, it will be helpful. And we will load the Tensorboard. Now here, what I'm doing here, it's only the global variables or global parameters I'm going to prepare it. What is the batch size, and what is the dataset size that we have, and what's the image size? Now, what is the batch size? What's the meaning of the batch size? We have the dataset size, it's 27,500 something image we have. Now, if we are going to process the full dataset immediately, it will be time consuming. It will be also sometimes maybe we will unable to do that because of the resources of the size of the memories and all of this together. And also we have another way to speed up the training, which is splitting this data set into batches, and then we will process the batch by batch. So what's we mean by that? The full model, we will train it for the first batch. That means the full batch. That means it will be the forward propagation, back propagation, make the training for it fully with multiple EBook. That means, and then we will start with the second batch, and then we will start with the third batch until we finish our data set. And this way, we are sure that first we are monitoring during the training, we are monitoring the performance of the neural networks, and then we can find maybe then sometimes we have to drop and stop the training. We don't need to continue, or we have some problems on the data. So this is better for monitoring the performance, and also it will be faster in training. This is how we can perform better in deep learning scenarios. Okay, so the image size, because our neural networks, it's expecting the input of 128 by 128 image. That means we have to resize all the images to this size to be able to process it. Okay. Now the class names, that mean it is our labels because it's supervised learning scenario. So we will use this as a class name just to say that if it's infected, the cell is infected or not. Now, don't ask me about the class name, why I use this. This is, you have to ask a physician about it, not a technical person. Okay. Now, I will speak about the display random image. It's simply, we just displaying some images that it's already segmented. That means we already know that this is only red blood cell, and it's only one red blood cell shown in the image. Just hopefully it's okay. This is a function just to display the random image. Okay, in this function we are doing something here. It's about the shuffle. Now, what's the meaning of shuffle? Shuffle is just like shuffling the playing card. That means we have to just randomly merging them because we don't want a kind of pattern appear when we are randomly choose the images. So we will keep that everything is random. Yes, Tom, please.
So just a quick clarification. This is of the images, the order the images come in, not of the images themselves, obviously. And then there were some private questions, concerns. Maybe, do people understand epochs yet? And Cyrus was asking everyone, does this mean that the total number of batches will be 27,558 over 64?
Something like that, yes. For this, for Cyrus, it's correct. Now, what is the EBook? I will stop here if you want, because right now it's only 15 minutes to finish and we can check the questions. I want just to continue about the augmenting, but we can keep it for the next week. No issues about that. I will speak about the augmenting before Sadiq starts. I will stop here and we'll check the question. And what is the EBooks, or what is the EBook in my accent? I will explain it now. Now, the EBook, it's the full run of the batch for training. How many times we are going to run this batch for training to the neural networks. So in fact, when we have this scenario, the neural networks, we have, for example, forget about the batch. Let's say we have the data set of 100 image and we want to train the neural networks to reach the accuracy of 99%, for example. Now, one pass, that means only running the neural networks for this 100 by one time and make back propagation, for sure, we are not going to reach the mean value that we want, which is reducing the error to the maximum, the minimum. So according to that, we have to run this multiple times. So for each time we are name it one EBook. So this is the EBook. It's the time, how many times, the total EBook number, it's how many times we are going to run the training until we reach our target, which is reducing the loss or reducing the error to the minimum. Okay, this is the concept of the EBook. Now the EBook, in our case, since we are splitting the data set into batches, it will be implemented for each batch. That means the first batch, it will run the full count of EBooks, and then the second batch, and again until we finish our batches. Now, I will check the questions, or Tom, is there something immediately I have to answer, or just read?
I think just read. And guys, do your best to pose questions. And we are trying to remember what it was like when we were first learning this stuff. But the important thing is to don't feel overwhelmed. Don't feel like you have to understand this all at once. Just understand we're taking windows across the data and we're doing certain operations with those. And those help us economize.
Sorry,
Oh,
Tom.
sorry.
This is a good example about the filter. It's 3 by 3 by 3. Okay. Now, if I have, this is my image, I'm just running this filter over the image, over each and every cell, and make some kind of function. Now, what is the function is no problem. It's depending on the task of the filter. Now, when we are implementing this to the neural network, we usually use multiple filters even. So maybe I will use 10 filters or 100 filters. So all the filters will be used to process the image. So I'm just making this and passing until I finish the image, and then I will go again until I finish the whole image processing. Now, what will happen when I'm doing that? Why the size it will be shrink? Because I'm for each pass, that means when the image is here and the filter is here, I'm getting from it one value. This is function at the end. I'm getting one value and keep it on one cell. Now, and then I will move it for a pixel only. Okay, since I'm moving for a pixel, so I have another row of pixel or another column of pixels involved right now. So I make the function and add it on another pixel. When I finish, I found that I lose at least one column by one row from the original size. Now, if I don't want to lose that, I can make padding, which is adding to the original image, adding zeros, one row of zeros and one column of zeros. In this way, the output of the convolutional neuron, the convolutional layer, it will be the same size of the original image without adding the zeros. But the main target of using the filters is to extract the features and reducing the size of the image to go for the fully connected layer. So using the padding, it will be much less. Most of the time, I'm not going to use the padding. I will use the original image. This is how it will work. Okay, I'm just trying.
So sorry, in effect, we're kind of taking a reverse look through a telescope, right? So we already know the bigger picture, and we're just trying to zoom in to that more finite point of data that we want. So it's kind of like reversing the telescope.
Now, if we are going to discuss about how the output of this it will be, in fact, you can find that no. Let's see this mobile phone. Mobile phone is appearing as a rectangle over the full image, which is my image right now. Now, when I adding these filters, some of the filters it will detect the vertical sides of the mobile phone. Other filters it will detect the horizontal sides of the mobile phone. Some filters it will detect something else. At the end, I will find that after processing for many times, I will find that there is some, at the end of the convolutional layer, at the end, maybe I can find that every circle, it will be appeared on one set of neurons, and other set of neurons, it will show only something else. Now, this is intuition. This is not accurate. But when I'm processing, now, if I'm looking for a mobile phone in the image, in the fully connected layers at the end of the neural network, it can get all of this information from the conv layers.
So just for management's sake, Guy, I think you're doing awesome here. Prioritize the questions that are written, and then we'll go back to hand-raised people. There's some really good questions, and some people already help answering them in the chat. I can help you manage them too.
We have a lot
go
of,
ahead.
Yeah, we have a lot of messages, so I need somebody to tell me.
I'll help you. So Greg wanted, can you explain how you got to picture size of 128 again in your example?
We didn't discuss about it yet. The resize method, it's not discussed yet. So excellent. For sure, I'm just adding the parameter, which is the image size. I need to reach that target, but still we didn't explain how to do it. And
then I'm paraphrasing. Can you explain the difference between batch and epic?
Okay, the batch, subset from the dataset. This is the most important thing. It's subset of the dataset. EBook, it's a pass. That means we are running the model and running the training method and make the back propagation for one time. So EBook, it's running the full functionality. The batch, it's subset from the dataset.
Excellent. And that covers a lot of questions. Does each batch have the same number of epochs? I'll answer that no. Epochs are how, how the network is being trained on that batch. It's an approach to a fit. Then batches, oh, Avinash's explanation, guys, is very good. So look at that. So in simple language, one forward and one backward pass of all the images in the neural network is one epoch. Yes, but usually we use a subset of all the images, which is a batch. Correct me if I was wrong, Guy.
Tom, yes, you are correct. Now we have, when we speak about the epoch, we have to think about it as for a batch right now. Maybe somebody is familiar to use it for the full data set, but since we are splitting into batches, so the epoch is something related to batch. By the way, thank you for correcting me, Tom. In fact, I never used different count of epochs for the batches. All the time I'm using the same count of epochs. So, but this is really interesting process. So I have to think about it.
In fact, all that we're saying, Guy's approach is fine, but if you're using a different method to say when you stop training, you can have different numbers of epochs. That's all that we're getting at. And Avinash has really been giving some spot on answers. So, and this last answer he gave, so batching is not the only thing. There are several approaches to train your NN faster. And I just want to add briefly, when we're talking about CNNs, we have a convolutional layer, and then we have the standard looking neural network layers. And what blew my mind when I was learning all this, I was learning the concepts, I was understanding the concepts, but then when I saw the details of how the back propagation even trains the convolutional layers, I went, whoa, that is so cool. And it literally, it's figuring out the filters on its own, guys. That's what's so amazing here.
Okay. Kind of visualization. Okay. Now, guys, I'm really sorry. The chat screen for me, it's very small, so that's why I'm suffering. Sorry.
I think we've covered it, but if there's any other questions, please hand raise, and I'm going to go mute.
Hand raise, or if we still have 5 minutes to go, and if we didn't cover them, we can answer on the Slack. Until I find the first hand raise, I want to mention something. Some of the videos, it will come from deeplearning.ai. It's from convolutional neural network course from deep learning specialization. Right now, it's restructured, and it's a great about the math behind it. It's really explained very well. If I want to explain it again, I'm able to do that, but not on that way. So that's why I choose to explain the concept. And for math, please go to that videos because it's really clear.
And when I was saying the filters, I meant the convolutional layers. They're kernels or filters that they act kind of like a filter to look for certain types of features, but they literally figure out on their own what kind of convolutional filters to add, what kernels, I should say, to add. Those kernels that slide over the image, there's a slick mathematical way that Jan LeCun figured out to train even those in the back propagation, which was a huge breakthrough, by the way.
Yes, Jaya.
Yeah, okay. So just a quick understanding. Say you have 100 images, right? And you're doing it 10 at a time. So that means 10 at a time, meaning that is 10 batch. I mean, that is one batch, correct? 10 at a time. And the epochs would be 10 because you're doing 10 at a time.
Now, I don't want to link anything related to the batch and the epoch. Epoch is different from the batching. The batch size, when we said it's 10 That means we have 10 batches. Each batch, it has 10 images in our case. Now the ebook, it's something else. It's something how for each batch, how many times we are going to pass the full batch for it. So it's not only limited to 10. We can use 40 batches, 40 ebooks, sorry. 40 ebooks, it's okay. It's depending on our task.
Okay.
Now, it's two different concepts, the ebooks from the batch. I hope I answered you correctly. What's the difference between them?
I think so. I know Avinash said one epoch is actually one full forward pass and then backward pass, right? So
yes. But this one full pass, it's for a batch, not for the full database.
I'll add something over here.
Yes, Ivanish, yes, please.
Okay, yeah. So the thing is, for epoch, if you're talking about the epochs, it's like how many times you want your neural networks to see all the images. So if suppose if I want to pass all the images, or let's say batches of images 10 times, so that is where you mentioned the epoch as n equals to 10 or number of epochs equal to 10.
Okay, exactly, Avinash. That's perfect. Exactly. Now this is not related. This is what I'm adding. It's not related to the batch size. Even if the batch size, the ebook can be 10, even if the batch size is 100, no issues. And even if I have 200 batches, also no issues.
But when we're talking about epochs, guys, we're talking about the training of each batch, just so you know. Now,
exactly.
If your memory can handle it, it's okay to train all the images at once, but usually that's not so practical. I think we better stop here.
Yes.
Guy, excellent.
Thank
It's
you.
a hard topic to lecture on, so good job, and we'll see everyone in mentoring.
Bye. Thank you, guys. It was amazing.